Here are the notes over exponential growth and decay. Now, we have been talking about exponential growth and decay, at good length already, which I'll go ahead and kind of review what we have talked about already. We've said that, hey, this is an exponential function, and A is the, I'm going to abbreviate it IV here, but we've been calling it the initial value. Well, today we're going to also call it the initial amount right there. As you can see, notice it's pointing to the A. That's great. And then what we've also said is that B here, if it's between 0 and 1, that was decay. And the idea is like, let's just take, for example, if you had 1/4 to the x power, well, okay, whenever you plug in x is 1, well, you get 1/4, and x is 2, you get 1/16, and x is 3, you get 1/64. Notice how this thing is seriously being chopped down to small really fast, so that's obviously decay. And then when b is greater than 1, that is growth. Okay, so that's everything we've basically known so far. And if you need an example of that, okay, 2 to the x has been our prime example thus far. So at 1, that's 2. At 2, that's 4, because it's 2 squared. 3 is 2 cubed, which is 8. 4, you get the idea. It's definitely growing, right? So now we're changing it up a little bit, and we're going to call B this whole thing right here, this whole group. That's essentially B, which is going to be our growth factor. And then there's a new element to that that's going to be called the rate of growth. Now, this should be fairly okay with you because, check it out, there's B, and if it's between 0 and 1, then our growth factor leads us to believe it's decaying. It's not really a growth factor, right? It's kind of the opposite of growth factor. And then if our growth factor was, let's say, 2, well, that's obviously greater than 1, and our growth factor is positive. Now, the reason we can talk about that is because we can now look at an example, like let's say we did y equals 2 times, let's just keep it simple, 1.5 to the x power. We could now figure out that, hey, listen, 1.5 is this, so 1 plus r equals 1.5. Solve for r, and you would get 0.5. So the rate of growth in this scenario is 0.5. And it says decimal form because that 0.5 is really 50%. And we'll talk about that in a little bit more here in a second. Let's do an example. A website has 500,000 members in 2020. The number of Y members increased by 15% each year. So let's go ahead and stop there. If we compare it to all of this, what we just said is the initial amount is 500,000, and it's going to grow by 15% each year, and we're going to do t for time instead of x. And then this is where I said we'd talk about percentages a little bit more because we don't want to write 15%, we want to write 0.15. So I did some examples in class where I was like, okay, if you had 25%, that is really 0.25, and the idea is that, yes, your decimal's right here, but you move it 2 places to right there. So you could write pretty much anything really quickly. Okay, 75% is 0.75, or 175% is 1.75, because you start there and then jump 2 spots to 1.75. If you had 3%, okay, well, you start here and jump 2 spots. So it would be 0.03. So that's a little quick percentage lesson in case you need a little refresher. So what we're going to have here instead of 1 plus 15% is we're going to have 500,000 times 1.15 to the t power. And now we have satisfied this part right here where it's write an exponential growth function that represents the membership. Now they want to say how many members will there be in 2026? Well, this represents 2020. So basically 6 years later. So what we're going to do is we're just going to copy this. Hang on, I copied too much because I wanted to change this to a 6. You know what? That works. That works out pretty okay. Now, this is where I recommend you grab Desmos, you grab a calculator, and you're going to type this in because 1.15 to the 6th power is, it's doable by hand, but gross. If you're not sure what I mean, I just did it on a calculator, and if we were to just leave the 500,000 part alone, 1.15 to the 6th power is 2.313060766, and I'm sure it keeps going. But now if I multiply that by 500,000, we get 1156530.383. Jacob, that was for you. So after 6 years, this website has grown by that, or up to that. It was at 500,000. So here, just some quick math. It grew by 600,000, 56,530. This is how much it grew by. Now the answer that they're looking for is that 1.1 million one. But I just figured I'd give you an idea of, yeah, if you grew 15% per year for 6 years, it would look like that. Now I'd like to stop. For those of you who are like, I guess I see that. How does this connect with what we've been doing? So what we've been doing is we would take something like y equals 2 to the x, and we would go, okay, well, it was here at 1. And then when x was 1, it would be 2. And when x is 2, it would be 4. And when it's 3, it would be 5, 6, 7, 8. It would be 8. And here at 1, it was negative 1, it was 1/2 and 1/4. And it looked something like this, right? So what exactly are we doing here comparatively? Well, now comparatively, we have to zoom out a ridiculous amount because we're not just doing 1. In this scenario, we did 500,000. So it's way up here. Imagine that's 500,000. And so the growth is like this. It's like, meow. And the reason I'm even drawing this is because there's the y-axis. So you'll have a tremendous amount over here that's way left of the y-axis. You know what I mean? And the growth is flatter because 1.15 is, yes, it's growth, but it doesn't feel like that much growth. And in case you're wondering, so here, I'm going to put a little chart on here so we can kind of see the comparison, okay? So imagine that we had 2 to the x and 1.15 to the x, and we just compare those just like that. So when we plug in 0, I think you know what we expect. We get a 1 there, and a 1 there, and that makes sense. Now if we plug in 1, so for 1.15, okay, now that's where we get that, but for 2 to the x, we get 2. Obviously the growth is fairly different when we plug in 2. For 1.15, we get 1.32. It's definitely growth, but over here we get 4. And then let's keep going. We put 3. For 3, we get 1.52. Now, by the way, there are some dots after this. There are some additional numbers. Not here, but for these two and everyone after that, there's going to be some significant decimal places. That's 8. Okay, and then for 4, we're going to get 1.75. There's some more decimals. And for this one, we get 16. These curves are just going to look a lot different. In fact, here, this is essentially, here's this curve. The red one is this one, right? The red one is this one. Right here is the red one I'm talking about. So now let me graph the other one. I'll graph it in yellow to kind of match this right here. So at 0, it's 1, just like that one. And then at 1, it's 1.15. So it's just a tiny amount of growth. At 2, it's 1.32. It's going to feel pretty flat. At 3, it's 1.5. At 4, it's 1.75. In fact, here I'm on Desmos. At 5, at 5, we finally get up to 2.01. So here's 5, we're at 2. So it's also going to have an asymptote of 0, but check out the difference in growth, right? This is still growth, it's just not quite as drastic as that one. And you might have thought, yeah, I know all that, but I just wanted to give you a visual. And really, when we get over here doing some more of these money problems, I'm going to show you some more like graphing visuals because I think it might be helpful. So determine whether each table represents an exponential growth function or an exponential decay function or neither, and then explain. So the first thing I'm going to look at is x is just fine, so I don't really have to like worry about it being funky. It's not like counting in a regular pattern, 2, 4, 6, 8 would be fine, 3, 6, 9, 12. I mean, stuff like that would be fine. Just, I'm just going to check. Okay, so here's what I'm going to do. I'm going to ask, okay, what did I multiply by to go from 270 to 90? Well, my initial thought is this is decay, and I'm going to put a question mark there, and here's what I'm going to do. 270 times what number gives me 90? Well, I divide both sides by 270. 90 over 270, that's 9 over 27, that's 1 over 3. Okay, so I just found out that that is multiplied by 1/3. So if this is going to truly be decay, from here to here needs to be 1/3, and from here to here needs to be times 1/3. And it is. 90 times 1/3 is 30. So there's 1/3. 30 times 1/3 is 10. So boom, 1/3 there. So this is decay, and it's because our rate, our growth factor, you could say, is 1/3. Okay, how about this one? Well, right now it looks like times 2 times 2 times 2. And I mean, that's, when it's growth, sometimes it's a little easier. Like if it hadn't been that easy, then I would have recommended you do this right here. So I'm going to do that again to go, hey, what happened here exactly? 5 times some number gave us 10. Well, okay, you divide by 5, divide by 5. It was 2. Well, 10 times 2, does that give us 20? Yes, it does. So this one was very easy, but you just should check each one because maybe they throw a little bit of curveball at you. I mean, what if you had looked at this and said, this is plus 5, plus 10, plus 20, and you didn't think about this part? That's why it is useful to do some little checking like that, right? Right. Interpreting exponential functions to determine whether it's growth or it's decay. You should be able to look at this and tell 100% immediately right here. This is our growth factor. This is our B. A is 5, B is 1.07, B is greater than 1, specifically just that part. So this is growth. This one, here's our A, here's our B. B is between 0 and 1, so this is decay. All right, so this section right here is going to represent kind of I don't want to say the trickiest part, but it's not going to be as straightforward as just, hey, tell me what A and B are. Instead, they're going to say, listen, we've given you this, we've given you this, and we want you to rewrite it. We want you to, there it is. We want you to rewrite this function so that it is a proper A to the bx looking function. Okay, and if you're like, well, isn't that a proper A to the bx? No, because there's stuff going on up there, right? So here's what we're going to do. We take some of our rules. In fact, let me grab those real quick. Here we go. We grabbed some of these rules because we're going to need them. So I'm going to kind of slide this over here. And the first thing I'm going to do is, okay, we have t over 4. Well, does anything over here remind you of like, we have something over something? And why don't you just take a second to look? I'll pause. Pause ending now. Well, here we have something where it's something over something. I should be a little more specific. We have an exponent where it's a number over a number. And that's what we had over here is we had a number over a number. So what we can do with that is we can say, all right, well, we have 100, because he's not affected by that exponent, times 0.96 to the 1/4 power, and then that is also being raised to the t power. And now here is when you're going to need a calculator. You're going to grab, so the fourth root, I'm going to put parentheses in my calculator, 0.96 raised to the 1/4 power, and I get, this is kind of funny, you get 0.989846. I'll write that out so you can see it. It's 0.989846401. I know you don't care about it being that large, or that detailed, so I'll round it to the nearest hundredth, so which is those two. So it's really going to be this, 100 times 0.99 to the t power. Well, you might have looked at this and thought, yep, that's decay, but this is the definitive, like, that's definitely decay because of the 0.99 part. Again, what did we do to get this? We rewrote this exponential part based off of these rules, okay? And we got this and this, okay? We put this yellow part in the calculator, which gave us this, and I rounded, and we gave our answer. Let's slide over here. Subtracting, t to the 1.1 to the t minus 3 power. Anything over here where they're subtracting? How about the quotient of powers? So what you could do is you could say, hey, well, we'll take this base right here, this a, and we'll put it on top and bottom and give it each of these exponents without the minus sign, so to speak. And if you're like, what is that? What are you talking about? So check this out. Here's what I'm going to do. 1.1 to the t power over 1.1 to the 3 power, to the third power. That's what is going on here. Is imagine we rewrote this part, and it would look like this, x to the 8 minus 2 power. So to go from this red box to this purple box, it's like we got rid of that minus sign, right? There's no minus sign right there. So that's essentially what we're going to do over here. And again, just like this other one, this part right here, in fact, here I'm going to highlight it so you can see what I'm talking about. This part right here, we're just going to put in the calculator. So this part right here, we're going to put in the calculator 1.1 to the third power. And I'm going to do 1 divided by that. And what I end up getting is, let me change the pen here, I get 0.75, I'm just going to leave it like that. I'm not going to write the other 6 decimal places. This piece, if I just took 1 over 1.1 to the third power, I get, and this is kind of hard to believe, you get 0.75, roughly. And then this guy's still on top, times 1.1 to the t power. This and this are the same. That's where this is a little funky, right? Because over here, I mean, I feel like you could follow me pretty well of like, oh, okay, yep, that becomes that, and this is just a number. So how did this 0.75 pop out front? Well, we rewrote this to its 2 separate exponents, and this is just a number. What is it? It's this, 1 over 1.1 cubed. So here's 1.1 cubed, which I'm telling you, the calculator says is 0.751314,801. And this is our answer. So this is definitely growth, and that's what lets us know. And that the fact that that is greater than 1, that's the confirmation. Okay, and now for the really kind of the, I feel like we were going in a straight line when it came to these concepts right here, and then we were going in a straight line, and then we zigzagged when it came to example 4. Now we're going to zag back to what I thought, Anyway, so it says solving real life problems, and here's what's going on. Compound interest. And also, this is when I said I would be giving you other examples. we're to the other example portion, because you have probably heard of compound interest. And so let's give some examples of what that looks like, okay? So I'm going to work this out. If you'd like to watch it and sit through this, great. If you don't want to, then, speed ahead to me doing this problem down here, okay? You'll know I'm down here because I'll be working down here. Otherwise, I'll be out over here in the void. So what's going on is, let's just talk about this first. Compound interest is earned on the principal and on previously earned interest. The balance of Y of an account earning compound interest is, so here's all this stuff. This is your account. This is how much money you got. This is how much money you put down, the initial amount, or also known as the principal. This one is a 1. And this is like this over here, where we are having a growth factor where it's 1 plus a number. So right here is 1 plus the rate, the annual interest rate, okay? But it's not just the interest rate. It gets divided by the number of times it is compounded per, what does that say, per year. And then up here, N, notice N is repeated. Oh my goodness, that's a little different. N, again, is the number of times interest is compounded per year. And then T is time in years. So what is this, what is this like? It's like this. Y equals A times B to the X. But now notice that the A and the P are connected. Those are the same thing. And now B is this whole thing right here. And what's interesting about it is part of this B actually shows up right here. And then this X, and this T are the same thing. So I'm just kind of connecting the dots of what we're looking at. So let's say you had $100. And what we're going to do is we're going to try and do this little chart here. In fact, you know what? Let's not do it like this. I'm going to do a Desmos graph. That's what I'm going to do. Well, it turns out I didn't do a Desmos graph. Instead, I did a lot of this stuff right here where I just went through and said, all right, listen, if you had annual compounding, then you would compound things one time. Okay, and so here's after 1 year, if you started with $100. So here's the idea. I've got some scenarios here where you've started with $100 and your interest rate is 2.5%. So your R equals 2.5%. And what that's going to look like is your account then equals, so let's do this. It looks like that. That is literally this formula right here, right? So let's go ahead and put in $100. So there's 100, parentheses, 1 plus, so our rate was 0.025, that's 2.5, over N, and then N times T right there. So T is going to change based off our years. N is the number of times it compounds. So this account equals all this. This is what I've done right here. So after one time, it's going to be this. So imagine you had $100, it goes up 2.5%. You'd have this much money. And then I said, you know what if I did it for 10 years? I'd have $128. So here's what that's going to look like. This one right here, if I did, it compounds once. So then, it compounds annually. Then what I do is I get rid of that and I write a 1 here. And really, let's be honest, 0.025 over 1 is just 0.025, right? And then I'm going to get rid of this. Oh, whoops, I didn't get rid of it. This N right here is also going to be 1 because it's going to happen how many times a year? Once. And then if I want to see, okay, so how many times, what would it be like after 1 year? Well, then I put a 1 right here. So this blue underlined equation right here is $100 at 2.5% interest compounded annually for 1 year. So here, let's actually zoom out and kind of add this right here. So in this situation, n would equal 1, okay? In the annual situation, n equals 1. And if you're like, I'm a little confused by all the stuff that's written here, the reason I did this is to kind of help give you an idea of, okay, semi-annually, you're going to hear that and you're going to go, well, how often is that exactly? It's going to be n equals 2. That's what semi-annually equals. So imagine that your $100 gets compounded once, and it's 102.5, and then twice, it's 102.52. And if you're like, what? I don't understand. Well, think about it. Compare. So here's like a little division line. Compare this right here, which was compounded once. Okay? And then now look to the right, where I'm going to write it like this. Let me zoom out a little bit so I can put it all in the same. So here's our $100. Here's the 1 plus. And then what we're going to do is our rate is still going to be 0.025, but it's going to get compounded twice. And really, if you think about this, 0.025 divided by 2 is 0.0125. It's actually technically a smaller growth rate, but here's the kicker. It's going to get squared now because that n is 2. This n and this n are the same n's, right? So it's going to get squared. And then this other part where it's going to, if after 1 year, is right here. So that's how these are similar, is this and this. And so if you compare it, your semi-annual, if it compounds twice, you get an extra 2 pennies, which you might think, well, whoop-de-doo. I don't know. It's a little interesting because then after 10 years, you get an extra 20 cents. Now, here's what I'm going to do. I'm going to zoom out a little bit and like make some more commentary as opposed to like whatever, as opposed to just saying, making a big deal about how much money you're earning. Quarterly, n equals 4. Because it's going to happen 4 times a year. Monthly, n would equal 12 because it would happen 12 times a year. Daily, well, I think you know how that would work. It would be n equals 365 times a year. And then, by the way, this one where it says infinite, this was just me kind of having some fun because this is a totally different formula, and you don't need to worry about that right now. But the idea is to check it out. You would make more money. So check it out. This, you would go up 20 cents compounding semi-annually versus annually. You go up 10 cents. So really you go up 30 total when you do it quarterly versus annually. You would go up 37 cents if you compounded monthly versus annually. You would go up full 40 cents if you compounded annually versus daily. And here's the thing. After 1 year, after one time, it's not that much. But after 10 years, 40 cents. Hey, that's a difference, right? So, okay, now where it really will kind of show a bigger difference is, let's say you do $1 million, okay? Because there's more decimals. So there's more place value, right? So compared annual to semi-annual, I mean, that's $1,000, $1,935 difference. If you do annual versus daily, it's an extra almost $4,000. And then if you do this infinite one, this continuous one, so to speak, it's an extra $3,941 compared to just annually. So anyway, if you're like, that's confusing, it was just me kind of showing you at a glance what happens based off of the different, number of times it's compounded. Okay, so here, a quick review of what I actually want you to remember from this, or maybe write down. Annual, n is 1. Semi-annual, n is 2. quarterly n is 4, monthly n is 12, daily n is 365. I didn't do weekly, but n would be 52, right? So because there's 52 weeks in a year. So now I'd mentioned that if you pause the video and you don't really care about all this stuff over here, that you could jump down here with us. Well, now we're down here. So we are going to do this problem where you deposit $100 in an investment account. So let's start like this. Let's start right there. Our account equals the principal times 1 plus the rate over the number of times it compounds, raised to the number of times it compounds times time. And now let's just start plugging things in. So you got $100. $100. I'm going to go ahead and do this because we're going to have that 1 no matter what, okay? And then you earn 6%. 0.06. And let's see. It's annual interest compounded monthly 12. And then that's it. So here we don't forget your t. So boom, we have just written a function m. Okay, so hang on. We want it to be m, and we want it to be a function. So I guess we'll actually get rid of this a, and we're going to call it m of t. M of t equals this. So this would be your final answer for part A right here. It also says, and I kind of ignore this, it says you also have a savings account with a constant balance of $200. So in that respect, if you need to, you can add 200 here. But A was about, this part was just the investment account. Write a function B that represents the total balance of the two accounts after t years, and then find and interpret B of 5. Okay, so what they're saying now is write a function B, so it's going to be B of t equals literally all of this. So I'm going to copy this here. Put that there. Plus our 200. And then what we're going to do is find B of 5. So what that looks like is B of 5 equals 100. 1 plus 0.06 over 12 to the 12 times 5 power plus 200. So check it out. The only thing that changed for B of 5 is we replaced the t right there. That's the only place it changed. And now you're going to grab a calculator because this is obviously quite crazy looking. And then just for fun, this, this part right here, just this yellow part, is 134.88500153, and then plus 200. So really the answer is going to be $334.89. We're going to round up. This is how much would be in your account after 5 years. So that wraps up talking about exponential growth and decay, the notes. Let me know what questions you got. See ya.